Hey everybody, today we're going to talk about making large polynomials. Polynomials generally have coefficients that are typical numbers like integers or real numbers, or you may think you're being exotic when you say that the coefficients and values that you plug into a polynomial are going to be complex numbers like 5 plus 2i. But it turns out that you can make polynomials whose coefficients and values are themselves polynomials. And then those polynomials can be in turn other polynomials that are in turn other polynomials that are finally, I guess you would say, parameterized on coefficients that are integers and values that are integers. And the reason that you can do this is that backing up a little bit, in order for in order to compute polynomials symbolically when the coefficients are integers, if you go back to high school and you do like the FOIL thing, first, outer, inner, last, and you combine the terms, in order to meaningfully combine the terms, you're relying on the fact that integers form this algebraic structure called a commutative ring. And a commutative ring is a very fancy term for some sort of algebraic structure that follows the basic rules of arithmetic that we all kind of understand on an intuitive level when we're in elementary school, like even before we probably even really go to school, we know that like 4 plus 2 is the same as 2 plus 4 because addition is symmetric, and another word for symmetric is commutative. And we also know that we can kind of group numbers in two different ways. So if I ask you what 3 plus 4 plus 8 is, you could compute the same result by first adding 3 plus 4, then adding 8, or you could compute 4 plus 8 and then add that on top of 3. And, that's the associative property. So going back to polynomials, symbolic polynomial manipulation only works insofar as the coefficients and the values that you're working with form a commutative ring. But what happens as a consequence of that, and I think it's like a fairly direct consequence of it, but I'm not going to go too deep on that. What happens as a consequence of that is that polynomials themselves form a commutative ring. So it makes sense that you could have a polynomial whose coefficients aren't just like a simple number type like integers or rational numbers or real numbers or even complex numbers. You can have the coefficients of your polynomial be polynomials themselves, and then when you evaluate the polynomial, you can use the same polynomial type for your values as you use for your coefficients. So with no further ado, I'm going to show you an example here. So I've got 3 different polynomial classes here written in Python. And my first class, sort of like the lowest level class, is just a simple integer polynomial. And I abbreviate that with IP. So like an integer polynomial with coefficients 1 and 2, where 1 is the constant term, 2 is the x term. That's the same as 2 times x plus 1. And if I look at IPB here, constant term's 3, the x term's 4, so that becomes 4x plus 3. If I multiply those polynomials, this is just like standard high school algebra, then I get that third polynomial, which I'm notating as IPC, becomes 8 times x squared plus 10x plus 3. And you can kind of see the FOIL action going on here. Like the 3 is really just the L part of FOIL. That's the last times the last. The 8 is the F part of FOIL. That's 2 times 4. And then this 10 here, that comes from the O and the I of FOIL. So 4 times 1 is 4, 2 times 3 is 6, 4 plus 6 is 10. So that's all pretty simple, but then we start getting more complicated because then we have polynomials of polynomials. And in this case, we're going to set our first polynomial to have the constant coefficient of our integer polynomial a, and then the coefficient of the term with degree 1 is going to be our integer polynomial c. And then you can see we kind of do a similar thing for the PPB, which is our second polynomial of polynomials. And then we make this third polynomial of polynomials, which is actually the product of those aforementioned polynomials. And when you look at this polynomial, it's it's rather complex because the coefficients of the polynomial, the polynomial variable here is p, and then the coefficients of the polynomial are themselves a polynomial expression over x. And then we get even more absurd here because then we make a polynomial of a polynomial with integer coefficients. And you can see that my code automatically computes this type string that says this is a single variable polynomial whose coefficients are single variable polynomials whose coefficients are single variable polynomial coefficients whose coefficients are integers. And everywhere I said coefficients, that also applies to like what values you could plug into the polynomial when you actually want to evaluate it. So here we get this expression for PPPA, and it's a polynomial in terms of Q whose coefficients are, it's really hard to see this. Whose coefficients are in terms of P, and those P-based polynomials have coefficients that are polynomials based in X. And then we start evaluating the polynomial. And this, I promise you, this is the most complex step. So we have our polynomial of polynomials, and we evaluate it using the value, which in turn is a polynomial of polynomials. And when we do that, we end up with another expression that is now only a polynomial of polynomials. You'll notice that there's no, in our previous polynomial, we had this q. The q's have been replaced by this polynomial of polynomials. Then we do that step again, except for this time, instead of plugging in a polynomial of polynomials, we plug in an integer polynomial. And now what we get is a polynomial with integer coefficients. You can see here that this is a single variable polynomial whose variables are just x. It's no more complex than that. I mean, the numbers are a little big, but it's some number times x to the 10th plus another number times x to the 9th plus another number times x to the 8th, and so on and so forth. And then we finally evaluate that using the number, this number, which I guess is like a billion or so. I can't count the zeros. But then we get this really big number for the final result of the polynomial. But the thing that made this all work, and this is sort of like the big takeaway from this, is that polynomials are commutative rings. They obey the same properties over addition and multiplication that integers do. So you can add and multiply polynomials and know that they're going to that the symbolic polynomials are going to obey the commutative property, the distributive property, and the associative property. And then when you plug in values, the resulting numbers are going to obey those properties, and so on and so forth. And in some sense, a polynomial mimics the algebraic structure of the sensible algebraic structures that you can use for its coefficients or its values. I hope that was interesting. I know it's a little weird.